Okay, so let me start with a simple sketch here. This is number one. And so here's the ground. And here's the person. And the person falls down from here to here. This is the displacement of the person. So let me choose a coordinate axis that points in whose positive direction is downward and whose origin is at the top of the rock. So to draw for number two, to draw a conceptual motion diagram for her downward fall. So this is free fall now, and so that's going to look something like this. Something like that, with acceleration down this way, and the way I have my axis pointing, that would be a 10 meter per second downward acceleration. From what height did she jump? I'm going to use the kinematic equation without time that says Vy squared is equal to Vy naught squared plus 2a sub y delta y. And I know that her final velocity is 5 meters per second. And her initial velocity is 0 meters per second. Plus 2 times the acceleration. Okay, so my acceleration is in the positive direction according to my axis. So that's going to be 10 meters per second times delta y in meters. So if I solve that equation for delta y, I get 25 meters squared per second squared over 2 times 10, 20 meters per second squared. Again, always check your units. This does come out to be meters. 25 over 20 is the same as 5 over 4, which is 1.25 meters. And so that's the height that she has above the rock. And that would be this displacement right here, 1.25 meters. Okay, number 4. How long was the woman in the air? I know what her final velocity is. It's 5 meters per second. And so a simple way for me to solve for her flight time is to use the Vy equals Vy naught plus Ay t equation, and realize that her final velocity is 5 meters per second. Her initial velocity is 0 meters per second plus 10 meters per second, that's my acceleration, times t. And so solving for that equation, I get t equals 5 meters per second over 10 meters per second, which is 0.5 seconds. She's in the air 5 seconds before hitting the ground. That's number 4. Number 5, draw a conceptual motion diagram as she contacts the ground. And so as she contacts the ground, she's initially going to be going fast, but she very quickly slows down, something like that. And so the direction for the acceleration on this one is upward. Acceleration is upward. Make sure you understand that. And again, the way to realize what the direction for the acceleration is to ask yourself, what vector do you need to add to this vector to get that vector? And the answer is that you need to add a vector that's in the upward direction to this downward guy to get a shorter downward vector, displacement vector. Number 6, estimate her acceleration, assuming a displacement over which she comes to a stop. And so let me assume that she has a delta y downwards when she hits the ground equal to 20 centimeters, which is 0.20 meters. And now I'm going to estimate her acceleration based on using this equation, Vy squared equals Vy naught squared plus 2 a sub y delta y. So I know that her final velocity is 0 meters per second. Her initial velocity is 5 meters per second just as she hits the ground, plus 2 times a sub y. This is what I'm solving for. And I've got a downward displacement, which is positive according to my axis, of 0.20 meters. And so I am going to get an a sub y of negative 25 meters squared per second squared over 0.4 meters. Okay, now this negative sign comes out of the algebra, but it's also consistent with the direction that I'm assuming here, which is upward. But since that's any parallel to my assumed positive direction, it's consistent. Okay, so 25 divided by 0.4. 25 divided by 0.4. 62.5 minus 62.5 meters per second squared. Again, check units, and I do indeed get the correct units here. Number 7. Use your estimated acceleration to draw a v versus t graph. For the woman, starting from her jump off the rock up to where she finally stops moving. Okay, that's not too hard. Basically, let me draw it like this. So this is time in seconds, and I'm going to make this be, that's 1 second right there. Let's say this is 0.5 seconds. And this is my v meters per second. 1, 2, 3, 4, 5. And so she starts right here and she ends half a second later right there. And here's the line, goes like that, and the slope of that line is, the acceleration during her free fall, which is minus 10 meters per second per second. Okay, now I didn't have this on here, but in class we also had a, if you will, an 8th one where we estimated her stop time after she hits the ground. After hitting ground, I'll just abbreviate that. And now, since I know what her acceleration is, I can use this equation again. Vy equals Vy naught plus Ay times t to estimate the stop time t. So the final velocity after she stops is 0 meters per second. The initial velocity right after she hits the ground is 5 meters per second, plus, okay, so this is minus 62.5 meters per second per second. It's the acceleration times t in seconds. And if I solve that, I get, as I did in class, 5 meters per second over 62.5 meters per second for the time it takes her to stop. And doing that calculation, 5 divided by 62.5, I get 0.080 seconds, which is in fact 80 milliseconds.